All right, let's try to do this crazy problem. It's been driving me nuts. We got this graph of the potential energy, and we got launched the projectile from the radius over here at RS with an initial mechanical energy of negative 2 e to the 9 joules. This tells us that, well, the total energy at any point is also equal to, actually I'll write that above here a little bit here. The total energy at any point during this thing is also equal to 2 e to the 9 joules, okay? Now, let's start with our original Ko plus UO is equal to Kf plus UF. Kind of just know that this is equal to negative 2 e to the e to the 9 joules. It's pretty nice. We can kind of even solve for Ko here because we have Ko plus UO is already given to us right here. It's negative 5 e to the 9, negative 5 e to the 9, and that is equal to negative 2 e to the 9 joules. Ko is equal to 3 e to the 9 joules, just in case we need this at some point. But really, we're trying to solve for this Kf plus UF. Well, we also know that Kf plus UF is also equal to negative 2 e to the 9. Okay, and so let's take a look at what UO. I'd like to know what UF is, so that way I can just kind of solve for Kf. That would be nice. Well, I know that UO is equal to negative 5 e to the 9. That's also equal to GMM over R. Isn't that correct? And we're asked to find the kinetic energy at R equals 1.25 RS. Well, this is actually RS over here, isn't it? So I'll put RS. This is regular all RS. And then over here, we're looking at UF being equal to GMM over, this would be 1.25 R, isn't it? Like if I put this back to an R, you can kind of see how, look, this is the initial U at normal R, and then this is 1.25 R. Well, what is R? R is just this. I think R is just literally going to cancel out, isn't it? So we don't even need to worry too much about that. But let's try this out. So let's divide these two equations by each other, right? And we get that negative 5 e to the 9 over UF is equal to, look, this cancels out, this cancels out, this cancels out, this cancels out, and we got 1 over 1.25, which is actually just equal to 1.25. Okay, so now multiply that by UF, and we get negative 5 e to the 9, divide that by 1.25 equals UF. Just a little bit of math over there. And that should give us the answer for UF. So negative 5 e to the 9 divided by 1.25. So yes, we have that UF is equal to negative 4 e to the 9. And if we plug that back into this, Kf minus 4 e to the 9 equals 2 e to the 9. And it turns out that the Kf is actually equal to 2 e to the 9 joules. Look at that. Awesome. Okay, good. So now we were able to solve for the first part. Great. Now here is the second part of the problem. It's a little bit strange. We have to realize that the turning point is when the kinetic energy is equal to 0. Well, when is the kinetic energy equal to 0? Let's remember that at any point during this time, the energy is always negative 2 e to the 9. So if K plus U equals negative 2 e to the 9, and K is 0, that means that U must be negative 2 e to the 9. This will give us, this will be able to give us our turning point. But here's the thing. We got to use this graph to figure that out. So this point right here is when the U is equal to negative 2 e to the 9, right here. And if we look over here, we're going to find that we are some certain distance away from there. We're given 2 notches, and then here we're given 1, 2 notches again, and then another notch. So this is actually 1 R, and then this is another R, and then this is 0.5 R. So if we add those up, we get 2.5 R. 2.5 R. All right, and that's going to be equal to, if we try to plug in that many kilometers, we should get that 7.1 e to the 6 times 2.5 gives us this many kilometers, 1.775 e to the 7th, I believe. And that's meters. Meters, not kilometers, so yeah. There we go. We were able to find the turning point and the kinetic energy right here. It's pretty interesting stuff. A little bit difficult though. Good Lord.